You have stuff for me. To your left, please. Really? Right. I can't seem to get the computer to play sound through the speakers overhead, so I'm not going to play it, but here are the lyrics. I really, really, really would rather be without Riemann. There is absolutely no reason for these sums to find these areas to be this hard. So I want to introduce you to the absolute best theorem in all of calculus in two different versions. I'll start with geometry again. I'm going to define a function as an area. F of x is defined as the area under the curve t. Okay, so we can't use x in both places, from 0 to x. So here is my graph starting at 0. See if I can figure out these values. What is the value for f of 1? Well, geometrically, that's a shape, right? It's a triangle. Even better. It goes out to 1. It's a right triangle. But if the x value is 1, then the height here, well, y equals t, so that's also 1. And if that's true, what's the area of this triangle? A half. But the formula for a triangle is half base times height, right? So I'm going to write it as 1/2 base times height, because the base and the height are the same. So what happens when I get to 2? It's still the whole triangle because I'm starting at 0. So the base is now this entire piece. And the height is the same as the base. When I get out to 3, now you'll notice I have not actually written the value of any of these numbers because I don't care. I want to go back up here. and ask for any x, what should I get? Wait a second here. Consider for me a little change in the value of f of x. If I change x to be x plus h, I'm going to make a really thin strip right here. And I could ask you, by how much does the area change? If I want to know the change in this thing, what am I doing? I'm doing a derivative. I know how to take the derivative of that. What's the derivative of that? Right, because the 1/2 times 2x is just going to give me x. Didn't I say up here in an integral the letter didn't matter? So isn't that expression the same as that one? Fundamental theorem of calculus, part 1. If f is a continuous function on the interval from a to b, and we define g of x to the integral from a to x of f of, I change the letter because I don't want to use the same letter in two different places. So this is just like we defined our f of t, our f of x in terms of t up above. Then g of x is differentiable. It has a derivative everywhere on this interval. And what's more, the derivative is just that inside function where I change the letter. So if I write a function, the integral from 0 to x, square root of 1 plus t squared dt. And I'm taking the derivative, asking what happens when I change x. Then I'm asking you to take the derivative with respect to x of this. That's going to depend on where x is, isn't it? Because when I take derivatives, my derivative changes depending on where I am in the graph. I get a derivative formula by simply copying this thing down, striking out the t, and writing it with an x. All you have to do is take that inside function, and you're done. Now, hang on a second. What the... The change in the area here is given by the value of the function that we're changing to make the area. This function is the change in this. When I take the derivative of this, I get this back. An integral as an area can be thought of as the sum of a bunch of little changes. All of those little bitty rectangles Each little rectangle is a change. Change in what? A change in area. I need you to open your notes to chapter 3, section 2, product and quotient. Which was September 19th. I drew a rectangle, didn't I? And at the top, I drew a little change rectangle. And we measured change, we measured derivative, like it was a little piece of an area. Isn't that what this little strip is? It's a little piece of an area. So the derivative of this function is given by this little bitty area. As the width gets smaller and smaller and smaller, the only thing that matters is how high we are. The change in this area function is given by a y value at this spot. The change in an area is the value of the function we're adding up. Here's a function that is defined as the area under this weird ass curve. E to the t squared. You have a calculator. Graph e to the t squared. I only care about it when x is bigger than 2. Because I'm starting my integral at 2. Because of the way I wrote it up there, I'm thinking about the integral from a to x, and I was starting on ab. So I really only care to the right side. I can make it go to the left side, but I have to rewrite my equation. This is a very, very steep curve. It grows really, really fast. So I like to know how fast it grows. Well, that means I want to know its derivative. All I need you to do is copy down the integrand itself. Replace the t with an x. That's it. When I take the derivative of something that's written as an integral, the integral sign disappears. I'm sorry. I haven't gotten there yet. Haven't gotten there yet. I knew I was officially old when AARP sent me a membership letter. I wasn't annoyed until they sent me a, hey, do you want to renew letter? All right, I'm old. But you know what they sent with that? They sent a magnifying glass. For all of you old people who need to carry around a magnifying glass in your pocket. Because this magnifying glass is made of plastic. And it's thinner than a credit card. But it's still behaving like a glass lens this thick. How? A guy by the name of Fresnel developed a lens that looks like this, which, by the way, if you drive down the highway, you might see these on the back of RVs because they blow up the view quite a bit, especially you've got that narrow lane down the back of an RV. If you're trying to see out the rear view, you need to make your field of view bigger. They also put these on top of solar panels to collect even more light. Fresnel came up with the idea, and he said, what I'm going to do is I'm going to imagine that I have this giant lens. And what I'm going to do is right here, I'm going to cut into a piece of glass, a thin channel, whose angle matches the angle at the top of the glass. But I'm not going to change the height. So all of these little grooves get cut in, looking like our little rectangles, don't they? Only the tops aren't flat anymore. This time they're angled. And they're angled so that the angle here matches the angle up here. And when I create that, I want to figure out how much light is being pulled in and show that the amount of light being pulled in by this little bit of grooved plastic is the same as being pulled in by that lens. So I have to add up all the optical distortion. And when I add up all the optical distortion, I create a new function. Called a Fresnel integral. Fresnel integral. And the only reason there's a pi in there is so that I can make this integral nice and easy to do, quote unquote. 0 is the left edge of my lens, and I'm going across to some point x. But what Fresnel actually needed to know, once he was able to show that this amount of light matched, was he needed to know what that angle was. If I'm just going from 0 to x, how do I change that angle as I go across? Which means I need to know how that thing changes. Take its derivative. What's s prime of x? Say again. X. That changes to an x. That's it. Yes. I have to have the variable as a bound because that's the way the theorem is stated. I am integrating from a number to a variable. Yes, ma'am. That's actually an interesting point. No, it doesn't. As long as my function is continuous from here to here, it could be 0, it could be 7, it could be -3. The number at the bottom actually doesn't matter. What does matter, though, is what I've got as that upper limit. This was done specifically for the purpose of this example. Crap. That's not the integral from 1 to x. That's from 1 to x to the 4th. If I change it from x to the 4th, then I'm not really taking my derivative in x anymore, am I? I want to know how it changes as x changes, not as how x to the 4th changes. But I like your idea. If I thought of this just as x to the 4th, then I could think of that as going from 1 to bleh, secant. Okay, well, then I can just make it x to the 4th, right? But the x to the 4th itself is going to change as x changes. I've done this before. You've done this before. Picture me standing here a little Russian nesting doll, I would take another derivative. This is a chain rule problem. It's one to stuff. But I'm not taking the derivative in that. I'm taking the derivative in x. So I really need to use the chain rule here. So when I do my derivative, which is really the derivative of g with respect to x, I think about taking the derivative with x to the fourth. And then I hear in the back of my head in my infomercial announcer voice, but wait, there's more. And along comes my chain rule, the derivative of x to the fourth. Yes. Now, again, I put the parentheses around the secant to remind myself that the 4x cubed is not part of the secant. I would tend to write the stuff that is not part of the secant in front, but that's just 6 of one, half dozen of the other. Regardless of what that bound is, if I'm taking the derivative with respect to that variable, then that's fine. That upper bound, we just called it x. Remember, my letters are fungible. I can change them. I could do a function like this. Let's see. We were just looking at, I put it over there, the integral from 2 to x of e to the t squared, right? Okay, I'm going to do the integral from 2 to w of e to the z squared dz. And I want the derivative with respect to w. I don't care what the letter is. This thing matches this thing. That's all I have to do. Which letter I choose to use is completely irrelevant. Questions? Yes, ma'am.
You did use x to the fourth,
Yes.
and then you did change
Mhm.
the one before that for the sine pi t squared over two. Whatever that limit with x to the fourth, how would you go about it?
Okay. Integral from 0x to the fourth sine pi t squared over 2 dt. I want to take the derivative with respect to x of this junk, right? So I'm going to do exactly what we just said. I'm going to think of this as an intermediate step. So I take the sine function and I replace the t with this. Sine pi x to the fourth squared over 2. And now the chain rule rears its ugly head, and I multiply by 4x cubed. The powers? Absolutely, you could write pi x to the 8th. Yes. I just didn't. I did the direct substitution. I didn't do any simplifying at this point. After reading through this a whole bunch and listening to a bunch of examples, I said to myself, oh, taking a derivative cancels out an integral. Mm-hmm. Well, what's the derivative of a constant? So if I did if all of these were numbers, if all of these were don't drop things. Integral from, let's see, it was 0 to 3 of x cubed minus 6x, right? If I ask for the derivative of this, the thing inside that set of parentheses is a number. It's negative 6.75. We worked that out on Monday. What's the derivative of a number? 0. The whole idea here is that I've defined a function using an integral. So there's got to be a variable for that function somewhere in the definition. That means it's got to be on the bound somewhere. Yes, ma'am. Well, if I did, then I'd have to take the derivative of 3. What's the derivative of 3? And then I'd be multiplying by 0, which would give me 0. Here I took the derivative of what I plugged in. Here I took the derivative of what I plugged in, but I'm taking my derivative in W. What's the derivative of W with respect to W? And back here in the previous one, I could say, oh, that's a derivative of X. The derivative of X. So I just multiply by a 1 on the end here. Yes, the chain rule always applies, but the derivative of X is just 1. I can be done. More. Talk to me more, people. Yes. No caveat, no nothing. As long as my function is continuous on the interval starting at A. Integrals work for continuous functions. And as far as I am concerned, that is where I will start and end. That is the rock on which I will stand. The hill on which I'm willing to die at this point. There are ways around it. Next class. Not even next court, not even tomorrow, but next semester, maybe further. Much more technical than I want to worry about. So if a derivative undoes an integral here, can't I say it the other way? That an integral should undo a derivative? Isn't that what we spent the end of chapter 4 talking about? Working our derivatives backwards? Fundamental theorem of calculus part 2. If f of x is continuous on AB, then the integral from A to B of f of x dx equals capital F of B minus capital F of A, where capital F of x is any antiderivative of little f of x. I beg your pardon? This problem took us almost a half an hour to write out all the Riemann sums, to do all the simplifying, to do all of that. We're going to do it in 4 lines. Using the ideas we had in chapter 4, section 9 of antiderivatives. What is an antiderivative for x cubed minus 6x? So that's 1/4 x to the 4th minus 3x squared. But wait. Plus c, right? Wait a second. Wait a second. There's an underlined word up above. Any. So hell, let's let c be 0. I could pick any value of C I want. I might as well use the easiest one. Some of you are looking at me going, how the hell do you know you can do that? Let's go ahead and put the plus C on for the moment. The very top of the screen, it says what I need to do is I need to take the upper limit, B, the lower limit, A, plug them in and subtract. So this is equal to 1/4, 3 to the 4th, minus 3 times 3 squared plus C minus 1/4, 0 to the 4th, minus 3 times 0 squared plus C. In that second set of parentheses here, what do I get? 0, 0, C. So the only thing that's down there is a C. Up here, I get 1/4 of 3 to the 4th. 3 times 3 times 3 is 27 plus C minus the C's cancel. No matter what value I pick for C, it's always going to cancel out. So I might as well just leave it off. Let C be 0 and walk away. I don't need it. Now, if you go back and look at Monday's notes, you will see that we had 81/4 minus 27, and we got negative 6.75. Two minutes start to finish versus 30 minutes of Riemann's sum. Now you know why I say I can do without him. The fundamental theorem of calculus says I never have to do a Riemann sum again, provided I can find an antiderivative. No. Because you gave me an answer with an X in it. This is a number when I'm done. This is the area under the curve e to the x. What's the antiderivative of e to the x? E to the x. So I get e to the 3rd minus e to the 1. You said e to the 3x. Not on purpose, but it is what you said. But you can plug this into your calculator and give me a decimal, right? I don't care what it is. This is fine. That's a number. That's the area. I'm done. Now, frequently, I will write something like this. When I said, what's the antiderivative? You all said e to the x. So I'm just going to write down e to the x. Then I need to tell myself, oh, you need to plug in those two numbers. When we did derivatives, we used a vertical bar. I wrote d dx, and then I evaluate. So let's use that vertical bar again. It's like I did the integral, so the integral symbol should go away. Now I need to stick these numbers in, 3 and 1. And I put the number on the top in first, number on the bottom in second, and subtract the two. This is just a shorthand notation. It's called an evaluation bar. Since that is in computer science and Unix called the pipe symbol, you'll sometimes see it called the evaluation pipe. This was a homework problem, the homework you just turned in. You were asked to estimate that area. The area under the graph, 1/x from 1 to 2. you're supposed to use 4 rectangles, right? I think that was one of the homework problems. And it was disgusting because you had to give like 6 decimal places and all that. Ready? Antiderivative of 1 over x is ln of x. What is ln of 1? So your estimates should be somewhere around 0.7. Because ln of 2 is 0.693147. Should be around 0.7. You'll notice I didn't even bother to write down the plus c. I don't need it. It's completely irrelevant. As long as I can find an antiderivative. I need my formula sheet. I ate it. What did I do with that damn sheet? Here it is. I can't do quotient rule to find an antiderivative with quotient rule. I don't know how to do that. But I got a pattern match, and this one's on the sheet. So I don't need to know some magical method. I say, oh, wait, this comes from my formula sheet. And now we come to the hard part. What are those sine inverses? All right, wait a minute. That's sine inverse of 1 over root 2 minus sine inverse of 0. I want an angle whose sine is 1 over root 2. Right. 1 over root 2. If I rationalize the denominator, is the same as root 2 over 2. That's for my unit circle. I recognize that one. What's the sine? What's the angle who gives me a sine that's root 2 over 2? Pi over 4. What's an angle whose sine is 0? Zero itself. But the sine inverse always gives me an angle between minus pi over 2 and pi over 2. So the only angle I can spit out that works is 0. The only angle I can pull out of a sine inverse between minus pi over 2 and pi over 2. I'm done. I don't have to worry about periodic behavior at all. Oh, that answers pi over 4. I'm done. I don't have to have all of these things memorized. What I do have to have is a pattern matching skill. I have to be able to go back and say, I know I've seen this somewhere before. Got the weirdest sense of deja vu. I've seen this crap somewhere. In order for me to do this, I need to take the antiderivative of the square root. Right, because I think of this as x to the 1/2. So I increase the power and divide by that new number. Oh. Now the problem is that I know these numbers suck. 5 to the 3/2 and 2 to the 3/2 are ugly decimals. I don't care. I'm done. That's an exact value. You're welcome to take your calculator out and approximate these decimals if you want, because I can do 5 to the 3/2 on my calculator. Five raised to the 3/2 times 2/3. There's my first number. 7.453559925, and it keeps going. I just ran out of decimal places on my calculator screen. 2 raised to the 3/2 power times 2/3. And now I can subtract those. Yes? I can say, okay, what I want to do is I want to take this number up here and subtract this number right here. There's my answer as a decimal. Why would I want a decimal here? Personally, I hate this answer. I'm much happier with this one, but I'm a math geek. Why would I want this answer? Potentially, but then I'll probably be able to round off somewhere along the line, right? If I'm actually doing this for a purpose, well, then I'll probably have an application with a certain number of significant figures, and I can round off wherever the sig figs tell me to. How do I know if I got it right? How do I check this work? Make sure I didn't cut somewhere. I make mistakes all the damn time. How do I know I didn't make one here? Let's graph what? Now, what do I do with that picture? My calculator will take an integral off the picture and allow me this number. If I put in the left bound being 2 and the upper bound being 5, you'll notice it even shades it in. I got the same answer. Second trace, option number 7. The reason I have the decimal is to check myself. I just have one problem. If you type ln -2 into your calculator, what happens? It barfs on you. It doesn't know how to do ln of -2 or ln of -4. because unfortunately ln of x is not the correct antiderivative. I must have the absolute value in there. The derivative for the antiderivative for 1 over x is ln of absolute value of x. In the previous problem, we didn't write that down. Why? We were doing from 1 to 2. Those numbers are positive. The absolute value is the same thing. By the way, this gives you a negative number. Why is that the correct value? That tells me why I got a negative in the first place, but why does that make sense for the answer? Why should the answer be negative, even before I do any calculation? Unfortunately, that's not the correct answer, although the boundaries being negative contribute to that being the correct answer. Not necessarily. 1 over x is under on this side. So the area I have found is under the x-axis. That's because, Gracie, that's because we're on the left. Because over here on the right, we do that. But over there on the left, yeah, I should get negative answers out of this.
Boundaries are where but it's negative. It's under the.
No. What's the antiderivative for x squared? When you raise a negative number to the third power, what sign is the answer? It's still negative. So negative 1 cubed is negative 1 multiplied by a third. Negative 3 cubed. But there's already a subtraction here, and I'm dividing by 3. 27 over 3. 9. It's minus a negative, so it becomes a plus. So the answer is positive, even though my x values were negative. Ah.
Like it's not. You don't have to put a negative outside because the bounds are.
As long as this is a left of that, yes. The following is wrong. This is wrong. Why? No. No, I did the antiderivative correctly. The antiderivative of 1 over x squared is minus 1 over x, because x squared is x to the minus 2. So when I do the antiderivative, I get x to the minus 1 divided by negative 1. So that's the correct antiderivative. But I did something wrong in even doing that. This function isn't continuous. 1 over x squared is undefined at 0. There's an asymptote in the middle of this damn thing. I can't do this problem at all. This entire thing is wrong. As soon as I write the integral from -2 to 2, I've gone over an asymptote. And the fundamental theorem of calculus says my function has to be continuous.
If it was like 2 to 4, like you can.
Absolutely. Absolutely. As long as I avoid the one place where this function is effed up, and that's at 0. What I did is write a badly defined expression. That thing, the integral from -2 to 2 of 1 over x squared, doesn't make sense. You shouldn't write it like that because it's unclear. That asymptote in the middle throws you out of the ability to do an antiderivative here. The fundamental theorem of calculus does not apply. But Mariah, you're absolutely right. If I went from 2 to 4, perfect. If I go from 1 to 4, I just have to avoid 0. Blake. Yep. As long as I am staying away from 0, this function is perfectly fine everywhere else. So as long as your interval does not include 0 for this function, you're golden. Which really means this expression there's only one correct answer. You can't do this integral. Period. So now the ground rules of calculus change. And my goal to find all of these integrals is to figure out how to do antiderivatives. We had enough fun doing derivatives, right? We had the product rule, the quotient rule, the chain rule, the trig rules, the exponential log. There were all these different rules, man. Now I got to do them all backwards in high heels. Makes it harder. But now that's really the rest of this textbook is how do I do these antiderivatives and what can I use them for? And I wish I was joking. But basically, everything in calculus from here on out is trying to figure out how to do this. The fundamental theorem of calculus is my best friend when I can find an antiderivative. Because sometimes you just can't. Here's a nice function. And I mean this really, really well. This is a lovely function. I adore this function. I would like you to graph this function for me. Once you graphed it, zoom in. Yes, sir. Yes. E to the minus x squared. Once you've graphed it, zoom in once. This picture is my friend. This is the bell curve. The normal distribution. All of probability and statistics bases itself on the behavior of this picture. And doing integrals from one point to another on this picture. Actually, they scale it just a little. So instead of doing e to the minus x squared, I'm going to divide this whole thing by the square root of 2 pi. It's just going to change the picture a little bit smaller. That's it. It's the only difference. I'm going to do integrals on this thing. A probability, the chance of something happening, is an integral. It's the area under this curve. From where to where? Well, I want my number to be between 1 and 3. What's the chance when I do this, the outcome is between 17 and 35? There's a procedure called standardization of data that moves from a bell curve with 17 and 35 to this bell curve. And then you do the integral in here. The entire field of data analytics is based on doing these integrals. Useless. I'm never going to see it anywhere. Every algorithm that runs your life is using these. But this function doesn't have a nice antiderivative. I don't know how to do the fundamental theorem of calculus on this thing. So how do I actually calculate those integrals for all that probability and data stuff? The only way I can. I'd love to walk away. I really would. Leave them in the dust. But there are more functions that I need to work with on a regular basis that I cannot avoid some variation on doing a Riemann sum. Questions? fundamental theorem of calculus basically tells me that what an integral does, a derivative undoes, and vice versa. What an antiderivative does is really an integral. Undoing derivatives gives me integrals. Undoing integrals gives me derivatives. The reason at the beginning of class that I wrote down these two names is because they get most of the credit. Isaac Newton, same guy from physics, studied at Cambridge in the 1700s until they closed the school. Why would they close the school? Oh, there was a plague. Everybody got sick. They sent them home. 2020, anybody? So Newton goes home and brings his notebooks with him and says, I've been doing all this stuff about optics. I'm going to create this methodology. I was listening to this guy at school whose name is Wallace, and the guy before him, Brown, and the French guys they were talking to, and the German guys they were talking to. And I'm gonna try and write this stuff, and I'm gonna write my book on optics. And he's studying prisms and the refraction of light. And there's an appendix to the back of that book called The Methods of Calculation, which will become, several years later, a separate book called The Principles of Mathematics, the Principia Mathematica, which is Newton's calculus book. Newton tries to publish this. But by the time he is publishing this book, what people are using this idea for is to talk about the position of the planets and the stars in the sky, assuming the Earth is not the center of the solar system, but that the sun is. There's this little problem. A guy by the name of Galileo. Galileo was excommunicated for the church for proposing this idea in the 1600s. They jailed him at home. The church did not apologize to Galileo until 1980s, when Pope John Paul II did it and reconciled the idea of science and religion working together, ex corde ecclesiae, on the building of Catholic institutions. Hi, Seton Hill. On the other hand, at the same time, over in Germany, Gottfried Wilhelm Leibniz is working on sums and accumulations and adding up all of these little areas. The church in England is pissed off at Newton. Archbishop of Canterbury, Bishop Berkeley, says, you expect me to believe that these minor changes, these fluxions, these departing ghosts of vanishing quantities should have any influence on our world? I say you consort with spirits and are a heretic. They try and have Newton burned at the stake for committing heresy. The Church of England is powerful at this point in time. The Archbishop of Canterbury is at the top of the bloody heap. Leibniz is German. He doesn't give a flying what the Church of England says. So he writes his book and publishes it. And all the people all over the continent, not on England, but all over the continent of Europe, take this idea, this antiderivative, this summation idea, and make it work. And then they figure out how it's connected to derivatives. And his version of the fundamental theorem versus Newton's version of the fundamental theorem become combined. I should have brought cookies, Fig Newtons and Leibniz biscuits. I should have brought them. Go home, have a cookie. I will see you all tomorrow. Have a wonderful afternoon.